All right. So we're very happy to have Hamsa Bastani from Wharton at UPenn, who is going to tell us about how to use Bandit for COVID-19 testing. Sounds exciting.
Thank you guys for having me, to all the organizers, and thank you guys for attending this talk. Yeah, I'm very excited to talk about some work we've been doing in collaboration with the Greek government for a large-scale Bandit implementation for targeted COVID-19 testing. This is joint work with Kimon Drakopoulos and Vishal Gupta from USC, John Vlachogiannis, who is our software architect, as well as a host of people from the Greek COVID-19 task force that I'll mention at the end. So just to kind of frame the problem, I want to give 2 or 3 slides about the background before I jump into the algorithmic design side of things. So Greece had a pretty tough time, as many tourist hotspot countries, when the pandemic hit at the start of the summer, because they basically had to balance keeping economic activity by allowing international visitors to come into the country versus managing the spread of the infection during this pandemic. And so 2 specific policy levers that we'll be looking at are targeted testing. So ideally, every time a passenger or a visitor comes into the country, we'll test them for COVID, and then if they test positive, we'll ask them to quarantine. But unfortunately, we just didn't have the testing capacity to do this. So instead, one option is instead to just go and selectively test passengers that we think are very risky and most likely to test positive, and then ask those people to quarantine if they test positive. So this will naturally be a sort of Bandit problem. And as a consequence of the kind of exploration that's baked into Bandits, we have the ability to basically maintain surveillance over different countries. So if a certain location starts looking, very risky, instead of wasting all of our tests on them and taking on the extra risk of these infections potentially penetrating into the country, we can actually make a policy decision to gray list a country. And that means for every passenger that's going to come in from there, we'll actually require a negative PCR pretest within 48 hours. And obviously, this is a big political decision, and it will affect their arrivals as well as the risk of people who are coming in. And these estimates basically inform those decisions. We've managed to gray list 10 countries over the course of this summer. But I'll mainly be talking about the first piece. And a couple of disclaimers. So this is a data-driven solution to allocate limited testing resources. Our goals are just to recommend who to test. We have very high compliance. Almost everyone we ask to test does get tested. And then identify hotspots to inform which countries are going to get gray listed and offer interpretable insights to the Greek government. What we are not doing is we're definitely not identifying all infected passengers. There's no machine learning algorithm that's going to let you do that. If you want to identify all infected passengers, you just have to test everyone. And we're also not optimizing for downstream contact tracing. Some of the information we're collecting gets passed on to them, but we're not optimizing for that in this decision-making process. Okay, so without further ado, here's sort of how the system works. So we have about 30 to 100,000 passengers who come into Greece every single day throughout the course of the summer. They can arrive in 41 different points of entry, so by water, by land, or by air. 24 hours prior to travel, each passenger will fill out a passenger locator form, which basically, or each family, sorry, which basically reports where they're coming from, various demographics and contact information and so on. The main feature of interest here for maintaining our risk scores will be the origin. So basically the country or the city that they're coming from usually informs us on how likely they are to test positive under a COVID test. And this all goes into our platform, which we've called Eva. And most of these people, unfortunately, will not get tested because we have limited testing resources. So they'll just go into the country and kind of enjoy their vacation. 6,000 to 8,000 of these people, based on our recommendations, will actually get tested. And the way that works is you step behind one of these curtains at the airport. This is a real picture. And then you get a QR code and it's scanned and it's linked to your sample with your passenger locator information. And then your swabs get sent to a lab. And then that information 48 hours later will actually get the lab testing results, which will feed back into our system. So naturally, by dynamically updating our risk scores using the most current testing results, we can maintain sort of the most updated risk scores and keep tabs of how the pandemic is sort of evolving in different locations, and use that to inform the next set of testing allocations. So this naturally has a Bandit flavor because we have Bandit feedback. You can't actually observe whether or not someone is positive unless you actually test them. Right? Okay, if there are any questions, please just interrupt me. So here there's a clear exploration-exploitation trade-off. On one hand, you want to test enough passengers from every arm. So here, when I'm talking about an arm, I'm talking about a location. So either a city or a country. More on that later. But just think of an arm as a set of passengers from a certain location. And then we want to make sure we're basically pulling enough arms, we're testing enough passengers from each arm so that we can estimate whether that particular location is very risky. And this basically will help us keep tabs of the pandemic. But ultimately, what we're really interested in is the exploitation part, right? So using these estimates to actually test arrivals from risky arms so that we can ultimately quarantine the most positive cases, so that the number of positive cases that are kind of slipping under the door into the country without quarantine is as limited as possible, so we can kind of limit the spread of the pandemic. Okay. So let me first talk about the algorithm design in terms of test allocation, and then I'll describe some of the statistical challenges that show up in maintaining estimates for each arm, or how we even define these arms. So now that we've kind of framed this as a multi-arm Bandit algorithm problem, you can basically use any Bandit algorithm that you want. You can use Thompson sampling or anything. We decided to use the optimistic Gittins index that was proposed by Guten and Furious with a one-step look-ahead window. So basically what this does is it computes an optimistic Gittins index that kind of balances an exploitation and an exploration term. So here, just for notation, Y is our prior. So we're actually maintaining Bayesian estimates of the risk for each arm. R is a binary reward. So for every arm, when we pull it and we test the passenger, we get binary feedback, like either they tested positive or negative. Gamma is a discount factor. So this first term here, expectation of R of Y, is just the estimated prevalence of that arm, of passengers from that arm. So that's our exploitation term. We want to test places that have high prevalence. And then we have an exploration term that kind of captures the uncertainty in our estimates to make sure that these estimates are actually good. Right? So I'll refer details to that paper, but if you use this algorithm, it's very simple. All you do is for every arm, you compute this optimistic Gittins index, and then you pull the arm that has the highest index, you observe the feedback, and then you update your prior, and based on the observed reward or feedback. So a couple very salient challenges in this context that made this sort of an approach very challenging was, first of all, we have highly non-stationary dynamics. So the epidemiologist basically told us any testing results that you collected that are more than 2 weeks old are basically useless, because if a location was safe 2 weeks ago, it doesn't mean it's safe now. If it was risky 2 weeks ago, it doesn't mean that it's risky now. So people kind of looked at the non-stationary Bandit literature, and there's sort of this forgetting principle, right? So basically, what we did was a very simple strategy. We're just maintaining a 2-week rolling horizon for our training data. So we don't use any testing results that are more than 2 weeks old. The sort of bigger challenge was that we also have a batch decision-making setting. So we don't get to dynamically decide who we want to test during the course of a day. We basically get the passenger manifest at the start of the day, and we have to make all of our testing allocation decisions. And then those are conducted at the airport. Even if we did get to dynamically update and it wasn't this batch setting, we would have another challenge, which is that we have delayed feedback. So once we decide to test someone, we obviously don't get feedback from them until up to 48 hours later, which means that even if we weren't dynamically making updates, we wouldn't actually get to see the test results within the same, when we go from one passenger to the next. And you might think, okay, 48 hours, 1 day, that's like 3 days. That's not a very long length of time. But actually 3 days is very long, given that our training data is only useful for 2 weeks and it expires outside of that. So that means that any exploration that you're doing is only valid sort of for 11-day window, which is not that long. And finally, we have port-specific constraints. So every port of entry has a different arrival mix from different arms and different testing budgets, which introduces a unique set of challenges. So let me first talk about the batch decision-making. So if you were to naively go ahead and implement this optimistic Gittins index algorithm, so here's what would happen. So I have 4 arms here. I've computed the optimistic Gittins indices. Arm one looks the riskiest, so I'm going to allocate a test to a passenger from that location. But then, of course, I don't get any updates because I'm not going to actually get any updates until 3 days later, right? So what would I do if I were to naively do this? I would just keep on exploring arm one while we're waiting for the testing results, which is clearly a very stupid strategy because I'll just pull a ton of people from arm one. I'll underexplore all the other arms, right? And this is really bad again because 3 days is a long time because the data is only useful in a sort of 14-day window. So people have recognized this. There's a big literature on batched bandits. So this problem turns out shows up in platforms all the time. And so I think a lot of the literature kind of follows an explore then commit type strategy. So they have sort of early exploration batches where they uniformly experiment across all your arms and they form good estimates. And then later batches just exploit based on that information. So this unfortunately does not work in a highly non-stationary environment because our old exploration batches quickly get discarded, right? So any exploration that we're doing on day one is only going to be valid for about that 11-day window, and then we have a rolling window. And so splitting batches up into exploration batches and exploitation batches is not a good strategy in this context. What we really need to do is to weave in exploration and exploitation within the same batch so that we're constantly maintaining this trade-off as we, gracefully roll our training data set. So how do you actually do this if you're not getting any updates? What we did was we used certainty equivalent updates. So what we do is we simulate the expected reduction in uncertainty from a test for a given arm. So let's say that we've given a test to arm I, and our Bayesian prior for that arm is say beta alpha I beta I. So alpha I is the number of successes and beta I is the number of failures. Once we give it a test, we're just going to add the mean number of successes that we're expecting and the mean number of failures that we're expecting for that one test to our successes and failures. Okay, so basically this will have the effect of maintaining the same mean, but reducing the variance as a function of the number of tests that we've allocated. Okay. And I'm going to call this a pseudo Gittins index to kind of distinguish from like actual Gittins indices. And these will naturally dynamically update within the batch, even though we're getting no feedback at all. So what does this look like if we go back to the same picture? If I have arm one and I pull arm one, once I actually allocate a test, even though I actually haven't gotten feedback on that test, I'm going to do a certainty equivalent update, which will then give me a new Gittins index, a pseudo Gittins index for that arm, lambda 1 prime, which will be smaller because it has the same mean, but it actually has a lower variance. Right? And so you keep doing this, and eventually, so for my next test, now we see that lambda 3 has the Gaia highest index, and so we'll actually change around our allocations during the course of the batch as a function of these pseudo Gittins indices. So I think this algorithm is pretty nice because it's very adaptive to the uncertainty of each arm. So essentially what it does is for every arm in the exploration phase, it allocates the estimated number of tests that you might require to resolve the uncertainty for those arms with high variance. So if you have an arm with very high variance, it'll get allocated a bunch of tests to resolve that. But if you have an arm with low variance, it won't get as many exploration samples, which is nice. And then all the remaining tests get allocated to arms with high mean reward, because obviously the first term of the Gittins index is the exploitation term. So if you have a high mean, you'll end up getting tests toward the end of the batch. So let's look at this on actual data. So again, this is actual allocations and arrivals data from our system for a given day, so within one batch. So let me just explain this plot a little bit. On the x-axis, we have the different arms. So again, like arms are locations, so they might be country or city identities. And here I've ranked them based on the risk level. So again, this is computed in an empirical Bayes way that I'll describe at the end. But arms towards the left side are very high risk and arms towards the right side are pretty low risk. And on the y-axis, what we have are the number of arrivals for that given day. So this obviously changes throughout the course of the summer, but this was what happened then. And you can see that the teal bars are basically the number of people from that arm that we have recommended to test. And the pink people are kind of the people that we've not recommended to test. And you can see that this algorithm has this very nice benefit, which is exactly what you'd expect. So it's easy to explain to policymakers. On the left side, you see that pretty much everybody is getting tested. So that's exploitation because these are high risk arms. We want to make sure we're testing all of them. If not, people will be very worried. But you see that pretty much every arm has a non-zero number of tests being allocated, even in the low risk category, because you want to basically make sure that you're doing exploration and surveillance throughout the course of the summer. You might look at the
Why is it that there is
Yeah.
such a big difference in the rightmost two bars?
These two, perfect. I was just gonna get into that. Great question. So the last bar looks a little weird because I basically said it's the lowest risk arm. And yet we're testing almost everybody from that location, which is weird because presumably you'd want to test only a small number of people for exploration. And this gets me to my next point, which is that we have port-specific testing constraints. So some ports only get arrivals from certain arms. So people coming in from the land border, for example, only come from certain countries. And they have testing budgets that are determined by the labs that they're contracting with. So the exploration-exploitation trade-off is actually pretty different as a function of the port, right? So let me jump into that, given that introduction, thank you. So the algorithm basically chooses the arm with the highest pseudo index and then finds a passenger on the passenger manifest to test. But passengers are coming at different ports, and passengers from some arms, again, are only traveling to certain ports. And then again, like I said, some ports based on their contracting have very limited testing capacity, which creates this weird consequence that you might actually want to save tests at certain ports for unique arms that will show up there. And there's been some work on bandits with constraints by Shipra and others, but it's still unclear how to sort of merge this with our batching procedure. So what we did was just a simple greedy heuristic. So whenever we wanted to test a passenger from arm I, we chose a visitor at the port that had the most remaining tests available. So basically we would preferentially test at less constrained ports in the hope that we can save tests for unique arms at very constrained ports. So just to summarize, let me show how the full algorithm works. So at the start of every day, we get the passenger manifest, we get the port-specific testing constraints, historical testing results for every arm. The historical testing results we then use to form empirical Bayes estimates, compute the optimistic Gittins index. We do the certainty equivalent updates for any pending tests from the last 2 days, which will give us our pseudo Gittins indices. And then we get basically two tables, right? So on the left side, I have different arms and I have their pseudo Gittins indices. And on the right side, I have the passenger manifest. So I see different arms, passenger IDs, which port they're expected to come into, and how many remaining tests are in that port. So what I'll do is first I'll say, okay, I'm greedy. So I'll just say, okay, arm 2 has the highest pseudo Gittins index. Give me all the remaining untested passengers from arm 2. So we see there's one coming into port 1 and one coming into port 3. Port 1 has a lot of tests. So I'm going to greedily pick port 1 and I'm going to test this guy. So I scratch him off the passenger manifest and I do my certainty equivalent update. So now arm 2's pseudo Gittins index has gone down. And now arm 1 is the riskiest. And you can see that arm 1, that guy's only showing up at port 3. So, good thing I saved my test for this guy instead of the guy from arm 2. Right? And then it proceeds like so on. Any questions about the algorithm?
I don't think it adds anything what I'm going to say, but I was just wondering, can we think of the different ports as like different players playing the same multi-arm bandits, and they each have like different arms that are open to them?
Mm-hmm. Possibly. I actually have not thought about that. Right. I think the challenge is that the challenge that we faced with trying to solve some sort of optimization problem across the ports was that the pseudo Gittins indices are being updated in the course of this as we allocate the test, and that's not closed form. So we basically struggled with integrating the LP with that updating procedure. But probably you could do something that incorporates the optimization directly. Okay, I wanted to mention two more challenges in this context, which is estimating the prevalence for each arm. So one really big problem with COVID in general is that the data is extremely imbalanced. So in most countries or locations, only 1 in 1,000 passengers is going to test positive. So this is a 0.1% rate. And these are kind of the safe locations. And what we want to do is amongst all of this, hey, we want to find the needles, which are 1% positive prevalence locations. So if you have about a 10 times rate, then that's what we qualify as a risky location. If you're anything more than that, like the US, for example, then you just get blacklisted and they don't allow you into the EU anymore. So that's one issue. And then the other issue is how you even define the arms. So I've just been dancing around between city versus country, but obviously as you define it in a coarser setting, like a country level, you incorporate less variance because you'll have more observations per arm. But if you have a finer level, like the city level, then you're going to incorporate less bias, but more variance. And so there's a bias variance trade-off to be solved here. So for the first challenge, what we did was we took an empirical Bayesian approach. So we're modeling every arm's test results as a Bernoulli because it's a binary feedback. And to do some sort of information sharing across arms to help us reduce variance, we assume that every PI is sampled from a shared feature-dependent prior, which we chose the conjugate distribution, which is the beta distribution. And the parameters of this beta distribution depend on whether the country is a whitelisted country or a gray-listed country, essentially. And this is kind of what our results, again, this is actual data. This is what our results look like. And this feeds directly into the Prime Minister's dashboard. Recall again that we're discarding any data that's over 2 weeks old. But on the x-axis, again, we have all the different arms. So these are country or city identities. And we have, and they're ranked by risk, right? So you can see that our mean EV estimates are decreasing. So the red points are the expected EV estimate, and then the dashed lines, the confidence intervals give you the 95% confidence intervals. And you can see that most locations look pretty safe. And then on the right, on the left side, we have a sharp kind of uptick where we see a couple arms that are starting to look very risky. And these are the people that we try to go out of the way to exploit. And you can see that we actually get pretty decent control over these confidence intervals, even though this data is so imbalanced, partly by using this sort of empirical Bayesian approach. Okay. So how do we deal with arm granularity? So there's only about 100 relevant countries that matter. So if you define your arms as a function of countries, then you get low variance because we get a lot of samples, but you might get high bias because there might be some cities that look very risky even after conditioning on the country that that city is in. But then you have thousands of cities, so there's no way you can allocate hundreds of tests to each city. So that's going to pick up high variance. So what we do to deal with this is we define most of our arms at the country level, but we try to identify some very risky cities that are risky beyond their country level risk. So what does that mean? We basically use lasso regression to identify a sparse subset of cities that are particularly risky beyond conditioning on their country's EV prevalence. So just to kind of visualize this, let's say that this box is one country.
I'm sorry, can I just ask you a quick question? I mean, here the set of arms is literally a magic space. I mean, it's actual places on the map. So we can, I mean, there has been a lot of work on exactly trying to, attack this bias variance trade-off as to whether you want to define, what kind of size do you define for your arms. So I was just wondering, so I understand maybe my question is very theoretical and you're trying to do something real. So maybe that's where there is a gap, but there are all those multi-scale type of approach where if you have a place where you don't have many samples from, then you want to have a big arm. And if you have a place where you have more samples, then you can zoom in more. Have you thought about using these techniques?
I think that's the same thing that the lasso regression does. Because basically it's trying to identify places that you want to zoom into if you have enough samples that it looks sufficiently more risky. I think we basically embedded it into a feature space that we thought made sense. There are sort of these non-parametric zooming algorithms, like you were saying. We didn't find the geographic, so you can also think about these things lying on a plane and you have the geographic distances between them. That actually is not at all informative for COVID because like two places might be close by and they might have urban versus rural. They might be mass complier versus not mass complying populations. So we didn't use that because it actually just wasn't informative, but the zooming is basically what the lasso is doing.
Cool, great, thanks.
All right. So I guess jumping off of that, so imagine that you have 7 different cities in a country, and these numbers basically represent what we think are our current empirical Bayes prevalence estimates in these locations. So you can see that 6 of these cities kind of hover around 2, and one of these cities looks very high, and it like looks around like a 5. Then what the lasso will do is basically it will group together the 6 cities that have similar prevalences. So you'll get one arm that's basically that whole country, and then you'll get another arm, which is that country minus that very risky city, which has a prevalence of 5. And this is very important because for the bandit, like when you're targeting this whole country as a whole might not look very risky, but that particular country is something that you would probably want to test everyone that's coming in. And then over time, as we get more samples and as we are discarding samples, we will update these arm definitions as we're sort of zooming in and out, right? Because this is a non-stationary problem. You can't just zoom in. You also have to zoom out sometimes as you kind of lose samples over time. Okay, any questions about the algorithm before I jump into the evaluation? Awesome. Okay, so a lot of people obviously asked us, okay, so you did this very complicated bandit thing, like was it actually more useful compared to a random policy that would just test random passengers? So we did this using, we kind of did this evaluation using off-policy evaluation with doubly robust estimation by Dudek et al. And we found that we got about 80% more positive cases than a random policy. So this number might still change because we're still actually running the system right now. But that seemed like a pretty decent lift. But we actually think this is a pretty significant underestimate because one of the things that we did throughout the course of the summer is every time we saw a country basically spike, we provided visibility to gray list that country. So what is gray listing? Again, it's when we ask, it's a policy decision where we would basically ask all passengers from that country to produce a negative pre-PCR test before they can actually come in. So this is what happens. So this is a particular country that I can't name that was gray listed on that blue dashed line. So kind of early August. And you can see that their prevalence was pretty high until they got gray listed. And then obviously after they got gray listed, it dropped a lot because now you can only enter if you have a negative pre-PCR test. So you're much less likely to actually test positive. Even then, some people test positive anyway because there's differences in testing accuracy and so on. The other unfortunate consequence is that the arrivals goes down, right? So a lot of people, it turns out, don't really want to go get a test. It's difficult to get a test, and so they might have to cancel their trip, or they might test positive. And so that's a big friction for people coming in. So this part of the counterfactual is a little bit harder to estimate because we don't really know what the prevalence would have been for a long time after the gray listing decision and what the arrivals would have been. But 80% is probably a significant underestimate because both of these things are at play. Other benefits are obviously, you have a dashboard. I think every government right now has like a dashboard in the pandemic, which helps solve various operational problems like determining the port testing budgets, identifying bottlenecks in labs. Like I said, we briefly helped out with the contact tracing. And so we had discussions with the Prime Minister, the Chief Epidemiologist, and the COVID task force every 2 days. So that's my co-author, Kimon, with the Greek Prime Minister, Kyriakos Mitsotakis, talking about this stuff. I'll just say one thing on public data. A lot of people have asked us, why do you want to do this complicated pipeline when you could just use public COVID-19 case or death data, which is publicly available? In fact, in most countries and the European CDC determine risk thresholds based on that public data. We've actually found that the public data is super unreliable. So here, every point is a country, and you can see the prevalence based on our Greek labs on the x-axis, and on the y-axis, you see the new cases reported publicly. You can see that the correlation is, you'd be hard pressed to say the correlation is positive. Even if it is positive, it's extremely noisy. And this is because the public data suffers a number of biases. It's also super delayed. So in the red line, we have the public data estimates for a particular country. And in the green line, we have our estimates based on our lab results. And basically, we can detect that a country is spiking like about 2 weeks before it actually spikes in the public data, presumably because the patient has to get has to get infected and then suffer symptoms, then get hospitalized before that data gets translated into the public database, whereas we see it right away when we test them. So obviously, if you don't have your own in-house testing solution, you're going to be allowing a lot of people from that country inside. And by the time that you actually catch it, it'll be too late because they'll have spread a bunch of infections, and then it'll be too late to control it at the border. So all this to say, we think you really need in-house testing, and this Bandit policy seems to actually produce a sizable lift compared to that. Yeah, and I just wanted to quickly note, there are a lot of people involved in this project. My co-authors, the COVID-19 Eva Executive Committee, as well as the COVID-19 Scientific Task Force, which involved medical school people, epidemiologists, and so on. Thank you. I think you're muted.
Thank you very much. Thanks a lot for the talk. So I'm sure there are lots of questions, and probably people will want to have a discussion on this topic. So I think we should keep the discussion to the discussion session, which is going to be after the next two talks. But is there a question maybe on like a very specific technical question right now? We can take one. But again, most of the discussion we'll just have it after the next two talks. Okay, if not, thanks again, Hamsa, and let's move to Yuanju. Yuanju, are you here?
Yeah, I'm here.
Perfect.